Gentlemen, I welcome you to this second invited lecture here at the AGI 2013 conference. It's a great pleasure for me to introduce Professor Thomas Glenn Dietterich. Currently, Professor Dietterich is Distinguished Professor of Computer Science at Oregon State University. He got an AB in Mathematics from Oberlin College in Ohio in '77, a master's degree in Computer Science from the University of Illinois, '79, and a PhD in Computer Science from Stanford University in the year '84. In his career, he held several positions, like a research assistant during your PhD time, an assistant professor at Oregon State University, an associate professor at Oregon State University, and since 1995, he's full professor for computer science at Oregon State University. Additionally, he was, for example, visiting senior scientist at the IIIA CSIC in Barcelona. He was chief scientist at several companies, for example, Smart Desktop and MyStrand Incorporated. He is the author of many papers and books. So, for example, he published more than 40 journal articles, more than 100 conference contributions, if I calculated this approximately correctly, 3 books and numerous book chapters and other contributions. His interest is primarily in machine learning, for example, for species distribution. He is also an expert in intelligent desktop assistants. I think today we will hear a little bit about this. He's also working in AI for computer games, machine reading and deep reading, in particular the extraction of information and knowledge from texts, and learning individual models from aggregated data, and many other things. He holds several honors. For example, he is an ACM Distinguished Lecturer. He's a Fellow of the American Association of the Advancement of Science. He's a Fellow of the ACM. He's a Fellow of the AAAI. And he's the President-elect of the Association for the Advancement of Artificial Intelligence. It's a great honor to have you here, and we are looking forward to hear your talk. The stage is yours.
Thank you. And thank you so much for the invitation. You know, I've always wanted to come to an AGI meeting, but it was always hard to find the time. So it's been very interesting to get to know a lot of you and understand better what the goals of AGI are. Because I think they're goals I share. So this talk is a reflection on, oops, keyboard focus, on a project that was conducted in the United States from 2003 to 2009 and was led by SRI International, which is in Silicon Valley, and then approximately 30 university subcontractors, and a few companies were involved too. And the goal was essentially to build an AI secretary, a personal assistant for the desktop knowledge worker. And so these are some of the functions that we wanted it to have. In trying to assemble the CALO system, they looked at studies that had been done about what do secretaries actually do, and then they thought about how they might be able to automate some of those things. So one thing they do is keep the user organized, and so the system should track the projects that a person has, the people that they work with, their calendar, the action items, and the various information products that knowledge workers produce, reports, presentations, papers, things like this. A major challenge for office work, especially with the desktop computer, is multitasking and interruption recovery. And so it should not be like the famous Clippy the paperclip from Microsoft Office, which was an excellent interruption mechanism that probably cost human productivity untold lifetimes. Another thing is that it should help with email management, of course, and then I guess the other thing here is scheduling and let's see if scheduling, resource allocation, coming to meetings and helping you understand the meetings. So we'll see how the system tried to achieve these kinds of goals. So the outline of the talk is I'm going to first, for the first, I guess, 10 or 15 minutes, try to show you a sort of day in the life of a CALO user. And then also take you a little bit behind the scenes and talk about how the CALO system learns from the user. That's all going to culminate with a description of the CALO architecture, which is maybe a somewhat generous name compared to the clean beauty of some of the architectures that have been described here today. CALO was much more like, I don't know, a favela or something that grew by just adding things on and lumping them together. So we'll say it's a very modular architecture. And maybe a very biological one in the sense that biology also tends to do things this way. And so I'll try to look at some of the reasons why that happened. I think there are actually good reasons for that modular architecture. And that modular architecture then leads to a problem, which is how do we get integration across the modules? And so we'll talk a little bit about some of the things we did there. Then I'll talk about things that were not done at all. That's the what's missing section of the talk. And finally, some discussion about could we have built CALO using different architectures and what would that have meant? So, a day in the life of CALO. I should note that this is, so CALO was a research system that was constantly being changed. So the slides here and the demonstrations, you'll see that they are different versions of the system. The story that I'm telling here never existed as one entire running system, but all the pieces did exist at some point in the 5 years plus of the CALO system. So let's imagine there's a boss named Helen. She arrives at work. And her computer shows her this thing which is called the Iris desktop. It's basically, Iris is basically a integration of the Mozilla mail system, the Mozilla browser, and calendar system. And then it also wraps around Microsoft Word, PowerPoint, Excel, and so on. The added value comes over here, whereas in this section, which is called the CALO sidebar. And it's where CALO keeps its information that it wants to tell you, its suggestions, and so forth. So in particular, CALO says there's an urgent email here from someone named Ken Rogers, a fictional person, of course. And CALO has predicted, it says, it is likely that you will respond to this email. It could really say within 4 hours, because that's our operational definition of an urgent email. And, of course, this is now available as priority inbox on Google Mail, Gmail. And it also tries to figure out whether this email has a meeting request in it or not. These are based on classifiers that were trained just by observing the user. If the user responds promptly to an email message, that's a positive example. If they never answer, it's definitely a negative example. And CALO has also predicted what projects are related to this message. And we'll talk a little bit about how that works later. But so it's predicted that there are 3 projects, the Gator, Optica, and UTIPA projects that are related to this email message. And the user, if they want to take the time, can click no here to say you're wrong, or yes to confirm. And they can also, the user can add another project if one is missing. And this is basically a supervised learning system that you can think of as a document classifier. It's initialized, though, using an unsupervised technique. So Helen replies to Ken, because it turns out Ken is a very important customer. He's actually the program manager at DARPA who's giving Helen all of her money. And so when he says he's stopping by for a visit, this triggers a huge amount of activity in the company to schedule things. In particular, Helen has taught her CALO in the past a procedure that she uses to schedule a DARPA PM visit. And she goes to her to-do manager and types in here SC and sees the matching things and clicks on this one, which is schedule a DARPA program manager visit. Now, a DARPA program manager visit, this is, we just had a talk on learning procedures, and a core, I guess, capability or competence where we spent a lot of time in CALO was trying to find nice ways of teaching the computer procedures. And so various kinds of programming by demonstration and programming by demonstrating and also explaining in natural language what you're doing. And I'll show you some about that in a moment. Anyway, the interaction that we use here is something sort of like a chat window. So this is called CALO chat, and Helen, who is this icon here, has just said, I need you to schedule a DARPA PM visit, and CALO, which is this orange C, says, please specify the input parameters for this procedure. This has been, was taught by demonstration, but CALO figured out in that demonstration what were the variables and what were the constants and what variables need to be specified. In addition, from the email message, it tries to fill out these parameters, but it needs some help. It didn't get the date or times right here, but it did get the day right. So Helen finishes filling this out and clicks the Submit button, and now let's look at what that procedure was that has been taught to CALO. So there are 7 steps. First of all, CALO is supposed to find a conference room that's available for the whole day and reserve it. And that's actually involves invoking another procedure to do that. And then we need to figure out, well, who needs to meet with this visitor? And to do that, CALO is supposed to look up the projects and subprojects that are associated with this program manager and schedule a meeting, say a half-hour or an hour time slot for each of those subprojects for them to brief the program manager. And the day should begin with a meeting between the principal investigator and the program manager, and the day should end also with a wrap-up meeting like that. And then we should include coffee breaks and lunch, and to do that, invoke another procedure called the catered meeting procedure to order those things for this visit. So scheduling a meeting, of course, this is just the main thing. This scheduling a meeting step is itself going to be quite complicated. But let's first look at step 2. How do we know which people and which projects are associated with this program manager? Well, one of the things a lot of CALO works on is trying to figure that out. So when you first install CALO on your computer, it does a sort of two-way relational clustering based on your email messages and the recipients on those messages, and tries to figure out, oh, here are the people that tend to be recipients together on an email message. That's looks like a project team. And what are all the words that are kind of shared among those, sort of builds a bag of words model of what that project is about. And using that, then, it initializes classifiers for the email and classifiers for the documents, and even tries to come up with a name for the project, which is often not that difficult, it turns out. So once those classifiers have been initialized using this unsupervised technique, there's actually a way for the user to interact with it and correct its mistakes. Then it continues to learn online as the system is used. And so one part of CALO's knowledge base is basically relational tables that describe who are the people, what projects are they on, what documents do they have that are related to that project, what email messages have they exchanged that are related to that project, and so on. Now let's look at so of course CALO can consult this information and say, oh, these are the email messages that are associated with projects where this program manager has been on the emails, so these are probably the people that person needs to meet with. Then the step 3 is done using another module of CALO, which is Emma, which is a calendar scheduling application. And a big challenge in scheduling meetings, I think some of you may have experience with calendar scheduling, and it's sort of notoriously bad in the sense that it's great for managers. They can force you to show up at a meeting. They just put it on your calendar. It's very bad for you, the victim, who don't seem to have any way of expressing your preferences. So Emma is really about learning preferences, and it can start by giving you example calendars and saying, would you like this meeting or not? And from that it can learn things like you don't like to meet in the mornings, you'd like to have an hour before lunch that's free, whatever. But it also learns from feedback. So then in the particular case we have here, we're going to make a request to Emma to put together a schedule. Emma's going to generate a schedule, and then we're going to give feedback and choose one of those schedules or even refine our request and go around this loop until we've got a schedule we like. Once we have that, then that's used as training to improve the preference model, and of course it also is used to actually as the schedule. So here are 3 schedules that Emma proposes, and unfortunately all of them have little warning signs on them that some constraints are violated. Actually, none of these really meet all of the constraints. So Helen can come down here and click on this Change Meeting Details button, and then go through all of the proposed meetings and say, well, we could delete this one is maybe not important, and maybe we can delete this one too. And so then Emma proposes a new set of schedules, and Helen says, okay, let's go with this one because it does satisfy all of the constraints. And then Emma can go ahead now and reserve the rooms and arrange the catering and add this meeting to everyone's calendar and send email alerts to all the invitees. So this is a huge time saver for anyone who's done calendar scheduling. So now Helen's got the current fire of the day, the pop-up problem solved for the moment. So she goes to her to-do list. The CALO has a fairly sophisticated to-do manager and has various ways of estimating for each of these things how urgent it is. And it notices that Helen is really in trouble today. She has 5 things she must do immediately. And so it suggests that she might want to delegate one of these things. And so it analyzes them to try to figure out whether they can be delegated and suggests maybe she could delegate this review insurance options task. It even is then able to say, well, who else in the organization might be competent to do this? And suggests Pauline Berry, or I can't read the other guy's name. But anyway, Pauline is going to get this task. So Helen clicks on this and says, yes, I'll delegate it to Pauline. Now, how did it know that Pauline Berry was competent to do this? Well, of course, another thing CALO does is, we'll skip that one. Another thing that CALO does is build an expertise model for each person in the organization. And this, again, is kind of a bag of words model. Actually, we do topic modeling analysis on all of your emails and your documents, and then can characterize different people by the topics they seem to know about. And then we can look at the topics that are in the insurance documents and say, oh, here's someone who knows something about this, or maybe attended some of the meetings where this document was discussed, and so on. So this procedure is completely hand-coded. Like many things in CALO, although there was a huge emphasis on trying to use learning techniques of various kinds to teach CALO as much as possible, there's still a lot of knowledge engineering in the system as well, and this is one example of that. Finally, Helen starts to work on one of the items on her agenda, which is finalizing a proposal for CALO Year 5. This is a very self-referential demonstration. She wants to let the other people involved in this know that she's running late, and so she can right-click on this thing, and a menu pops up, and she can do various things here. She can try to delegate it to someone, for instance, but she chooses notify related people, and then she's able to compose an email message right here, and the to-do manager knows who are the other people on the project, so she doesn't have to fill out the recipient list. So this is a minor speed up, but it does avoid having to switch windows and bring up your mail program and that sort of thing. Okay, well, now we come to Helen actually needs to open the CALO proposal and start reading it and editing it and so on, and then uploading it to the web page for the company. And this is a point where CALO tries to see whether it can help. So I mentioned CALO has been taught a lot of procedures. Some of those procedures are ones that CALO can basically perform on its own once it knows the parameters. We just saw that for the scheduling procedure. But there are other procedures where it's really a mixed initiative procedure. The person has to do some steps, then maybe CALO can do some steps. And that's the case here. And so there is an activity recognition system called WARP, that's another component, that is always watching what the user is doing and trying to recognize, is that one of the known workflows that I know about and maybe I could offer to help do. This is coming dangerously close to the paperclip, but it doesn't hop up and wave at you. So I'm going to show you, basically these procedures are represented as a probabilistic finite state machine. So you probably can't read this, but it says something like open the email, either get the proposal, the top path here is proposal editing, get the proposal, edit it. What does that one say? I can't, something about it. Okay, and then finally decide whether you want to get more feedback or upload the proposal to the website and notify everyone that it's done. The bottom branch is more for reviewing a paper, say a journal paper, where you have to get it, open it, look at it, fill it, get the review form, edit the review form, and then submit it. And so the problem is to figure out which branches, and obviously CALO is incapable of editing documents, at least intelligently, so those are steps that CALO can't do. Okay, so when Helen opens the email, CALO's activity tracker, which is, you can think of it as kind of like a hidden Markov model. It's trying to track and do state estimation. It's complicated, though, by the fact that Helen at any point can stop working on this, and because she'll get interrupted and have to do something else. So it's like tracking many, many HMMs that are all in various states of completion, and some of them will never get picked up again. Anyway, she opens the email, and so that matches the first state in this procedure, and this is actually what launches the activity recognizer. Says, oh, I've got my triggering state. I should see if this is something I know how to handle. Of course, this gets triggered every time she opens an email to read, so that it's going to be disappointed most of the time. Now she opens the attached file, and that means she might be doing either one of these two procedures, and there are probability estimates here about that. Then she starts to edit the file, and the activity tracker says, aha, I know now that she's doing the proposal branch, because you don't usually edit a paper you've been sent to review, much as you're tempted to sometimes. Then Helen closes the file, and at this point, CALO can see that there is a path from the current state to the end of the procedure that it could do everything else. So in the CALO suggest sidebar, it offers to complete the procedure and upload the document to the website. And so Helen decides to do that and accepts that offer. And so then she gets a confirmation in the web browser that the document was uploaded. So that's an example of this activity tracking and then trying to offer assistance when it can be done. So the next thing on Helen's to-do list is she needs to attend a meeting that's some sort of DARPA IT review. One of the interesting things that we decided was something that was really missing from the current desktop experience is something we call a prep pack or a preparation package. When you go to a meeting, it would be nice if you had a little folder on your computer, or maybe nowadays on your tablet or something, that had everything you really were going to need for that meeting, so that you don't have to the meeting doesn't have to pause while you dig through your computer trying to find that document that you need. And so the idea here, in this case, the user interaction is we actually have there's a little CALO box down here in the I think this is called the system tray, and so you can drag a appointment down to the CALO box, and it will pop up a thing saying, what do you want to do? And she can say, I want to have a prep pack for this meeting. So now CALO has to know what this meeting is about, who's invited, and things it knows from when the meeting was created. And so it can find what are the documents relevant to that meeting. And again, this will be based on knowing what project this meeting is related to, and therefore what documents are probably relevant. If it's seen the agenda come through email, then it can use that, for instance. So it displays this prep pack in a customized browser window you can see this is Windows XP, where there are 3 things that it has decided definitely should be in there. And then it has a bunch of other suggested documents. And if the user wants, they can click on some of them and say, remove them from my prep pack, and keep all the rest. And so again, this provides training data for prep pack construction. So now Helen goes to the meeting, and so far the basic concept of CALO was it is like this personal assistant that you get when you first join the company, or maybe you can even take it from one company to another, I don't know, that stays with you and learns your preferences and so on. The one place where this breaks down is when you need to interact with other people, particularly in a meeting setting. So there's a separate kind of team CALO that is used and we call it the CALO meeting assistant. And basically, when you attend a CALO-assisted meeting, everyone wears a close-talking microphone, and you don't all have to be in the same physical meeting room. And then there are various experiments over time, but the general idea is either a tablet or some kind of digital paper. And everyone has a smart pen so that as you take notes, those notes can be captured by the system, along with the exact time that you took them so they can be time synchronized with the speech transcript. Video is also taken, not because you'd really want to watch the video of a meeting afterwards, but to try to recognize the gaze and the gestures, so that if I look at Marcus, of course, since he's the stand-in for everyone, and say, so you will take care of this, right? And he nods his head, yes. We want to recognize that gesture and know that he is responsible now for this item, even though the speech transcript doesn't contain any meaningful information about that. So after the meeting, it's possible, if you missed the meeting or even if you attended it, to go to this meeting browser, and the meeting has been segmented, again using topic modeling techniques. And then there's also was quite a lot of work trying to teach it to recognize when decisions are made in the meeting and action items, when an action item has occurred. And for an action item, they try to extract 4 things, which is a description of the action item, the deadline by which it is due, the person who's responsible, and then the sort of the person they will report to when they've completed the action item. And so in some versions of the system, these automatically got added to people's to-do lists. In others, you had to agree to it, which also gave some feedback about whether it had been correctly interpreted or not. Finally, Helen needs to assemble a PowerPoint presentation about something called the PLOW framework. And so CALO has a sort of desktop search component to it. And in particular, so she finds a relevant PowerPoint presentation and then starts to edit it to make it into the one she needs. And she sees that the diagram on this slide is wrong, and she wants to look for another architecture diagram. So you can click on this on the icon down here, and you get this CALO search box, and then you can type in a natural language query like slides architecture diagram, meaning I want slides. And one thing that I'm really astonished that Windows doesn't already support is the ability to basically treat individual slides of presentations as first-class objects and be able to search them across all of your PowerPoint presentations, or your I can't remember what's the Mac presenter, but yeah, your keynotes. I mean, you know, it's crazy that you end up opening all these files and leafing through them trying to find things. So so based on keywords, then it presents these, and again in a modified Windows file browser, it's taken thumbnails of each of the slides of every presentation it knows about, and then it can analyze all the text on them, of course. So it suggests these 4. Helen says, well, actually, none of these are quite right, but this is the best match, so show me more like this. And then she gets some more like that, including one that's clearly like totally wrong. It's not even a diagram. But here's one she wants, so she can select this and then say, add this to the presentation I currently have open, and it will add it, maybe in the wrong place, but it will add it. So, so that's the kind of user experience that we were going for. And I think if you look at it, you'll see that CALO isn't like this little robot helper that's beside you at the desk. There are really sort of 3 different personalities or manifestations of CALO. One is really an agent, which did these, the to-do manager, the calendar manager, and the thing that's doing the activity recognition that really has goals of helping you and is watching your progress. But then there are a set of information management tools that are basically passive. They wait for the user to invoke them. And this would be things like the Iris desktop, creating the prep back, doing this slide sorter thing. CALO didn't figure out that you needed a slide and say, oh, here's a slide you might like. We really left that up to the user. There's a lot of AI in those. There are document classifiers and models of people and projects and so on, but it's a personal information management kind of thing. And then finally, there's the CALO Meeting Assistant, which is something completely different, mostly focusing on trying to understand interactions between people and their speech and so on. So that's sort of the user level view. I want to take you behind the scenes a little bit and talk about at least 3 of the different learning modalities here. So one is, of course, learning from user supervision. Well, let me interrupt myself for a second. I forgot. So here's sort of CALO's relational schema. So CALO's view of your world as a desktop knowledge worker is that your life revolves around projects. And then those projects involve people, they involve documents, they involve meetings, the people are invited to, and some of them attend the meetings. The projects also have lots of email messages with attached documents, and people have email addresses and people's names and things like this. So some of the same distinctions that came up this morning in Stu's talk are relevant here. So this is basically just the relational schema. The main thing I want to point out is that all these red links are ones that CALO has to infer, including figuring out what people exist, because people have multiple names and multiple email addresses for a single person. And the ones with the asterisks are ones where it's actually basically supervised learning that learns to do those. Okay, so we've already seen explicit training and feedback. This is pretty garden variety classification technology. Then there's implicit training. We saw some examples of that with the email urgency and your calendar preferences, where your decision to reply to an email message or to accept a calendar appointment are indirectly ways of expressing preferences over things that can be used for training. Then probably the most interesting thing, I think, coming out of CALO was this procedure learning capability. And there were several parallel efforts that were funded. I'm going to show you my favorite, which is the work that came out of the University of Rochester on learning by discussion. And so I have a video to show you, and let's see if I can get this to work here. We had a lot of fun during the break. Okay, so put this up here. I drag it over here. I double click it. Oh, I forgot. Well, I'll just explain to it. So this is a screen capture, and you're going to see in this part of the window is a modified Firefox browser that's been instrumented. You know, when we think about sensors and effectors, the sensors and effectors are mostly instrumentation and actions that have been integrated into desktop applications. Down here in this box here, you'll see the speech recognition output as it's trying to recognize what's going on. Up here, you'll see the procedure that's being learned, the sort of code for it. And down here will be a sort of history of the dialogue. And let's give it a whirl here. Whoops. Okay.
Let me show you how to find restaurants near an address.
Can you hear this?
Okay, go to this web page. Show me. Put restaurants in the place name field. Alright. The street address goes here. Okay. The city goes here. Alright. The state goes here. Click the search button. Alright. Here is the list of restaurants. Can you check that I understand the information? Here is the name. Show me. This is the distance. Okay. Keep the restaurants closer than 1 mile. Alright. I'm finished with the demonstration. Okay. Let's practice.
It's my favorite line. Let's practice.
What is the state address of the city?
So it's inferred what the parameters are that it needs.
All right. I am finished.
Okay, so that's the PLOW system. Whoops, did I? And let's see, I have to kill this window. Don't I? So a couple of things to note about it is that one of the big challenges in programming by demonstration is trying to figure out which of the things you're demonstrating are really variables and which are constants. And another challenging thing is teaching loops. The first work in programming by demonstration required you to execute the loop at least twice so that the computer could detect that it was a loop by matching things to each other. And so they really wanted to avoid that here. And one of the beautiful things about combining the narration with the actions is that some very simple rules really can solve answer those questions. So when the person says put restaurants in the place name and then puts the word restaurants, you know that's a constant. Where they say, and then put the address here, and they type a street address that isn't the address, then you know it's a variable, right? Because it's cued by these linguistic cues. Now, the complex iterative procedure, fundamentally, that's a very difficult problem. Here, they've kind of gotten around it by treating it as in a sense, vectorizing it, right? So the query returns a list, and we're able to, they added the ability for the user to select an entire region of a web page. You notice that he drew sort of a little rectangle, and they inspect the DOM, the document object model for that web page, and that selects a whole node in the DOM. And so you can select a whole list very easily and say, this is the list of results. And so that makes it possible to sort of realize that there's a loop, and now you're going to want to operate on all the elements of that list just by showing the information for each one. And of course, one of the beauty of these kinds of web pages is that they have a very repeated structure. So if you've learned to extract the distance to the restaurant from one of them, you can get it from all of them. So the nice thing here is that we're really able to teach the computer a complex iterative procedure without even going through the loop once, because the structure is made apparent. Now, of course, there have been several CALO spin-offs. One of them, of course, is Siri. I see my animation's messed up, which can do the same use case. I found 15 restaurants fairly close to you. I asked it this just before I was getting on the airplane the other day. And Siri was produced by a group of people that had worked on the CALO project, although I don't think there are any lines of code that are shared. I hope not. And then Smart Desktop is a company I was involved with that worked primarily on this email tagging and relating email and documents to projects. Email documents, people, web pages, file folders, email folders, all of those things. There are a couple of other companies that are currently out there in startup mode, Trapit, Tempo AI, which is a version of the calendaring ideas, and something called Kawato Studios that's games with a purpose outfit. And then, of course, this was a DARPA-funded project, so there are also several applications of it inside the Department of Defense in the U.S. Okay, so that's the sort of what the system was. Now, what about the architecture of the system? In what sense is this? How does this relate to general intelligence? You could say, well, this is a giant knowledge-engineered, stack of modules, and certainly it was a modular architecture. So this is the kind of picture we draw, where we have basically the three main sets of modules: the meeting manager, which then has subtopics like handwriting and speech recognition and activity recognition and detecting user agreement. The task manager, which had like the to-do manager and the meeting scheduler and so on. And then the information manager, which had various things like email management and desktop search. And then there were some integrating components. Of course, if you pick up an AI textbook, at least Russell and Norvig, you'll see a diagram like this, which is much more of a unitary architecture that says, well, we get in percepts. From those, we try to estimate the state of the world. Then we use our probability distribution over states and our utility function and our action models to choose an action to execute, and then we execute it in the world. Why didn't we develop a unitary architecture like this? And would that have been a good idea? So I think there are several reasons why we didn't. The first was that we really needed to take a divide and conquer approach when you have a project that involves 30 different subcontractors building different parts. But that's kind of the easy answer, is that it was a management necessity. But maybe there are some deeper reasons. One is that you can see the CALO system perform many different functions, and it had to be usable by a person. Those different functions, say calendar scheduling and so on, each of them required a different user interface that was customized to that task. And that meant that the perception and action involved interacting with that user interface. And so I'll talk about these points in a moment. So first, the management challenges. I already said all this, I guess. But I just want to raise the issue of whether there is a biological analogy. I mean, I think when we see the repeated structures in the brain, we're always reaching to say, well, there's only one algorithm and there's one unifying structure. But in general, biology does not work that way, right? Biology is full of duplication and hitchhiking and specialization after duplication and patching things on. And basically, if a hack works, it gets preserved and goes on to the next generation. So one argument is, any kind of robust system that's really going to live for a long time and improve over time, particularly if it involves people and interacting with them, is going to be messy. And so I think it's an interesting challenge. In AI and even in AGI, we still kind of think that we build the system and then it's going to run for a while on its own. And I would ask, well, how long really do any of our systems run? Long enough for the demo? That CALO basically satisfied that, more or less. So let's come to this question of functional decomposition. So many functions in CALO basically required special user interfaces because it's sort of like having customized tooling for a robot, right? Calendar scheduling should really use a calendar user interface. PowerPoint presentation assembly should use something like a slide sorter interface. A meeting browser should be something like a timeline, and so on. And so that really leads to, in a sense, for each different case, you have a different set of perceptual apparatus and a different set of actions that can be taken. And so we could have had a unifying sense-act cycle. What is the lowest level sensing in the computer? Well, it's the keystrokes and the mouse clicks and mouse motions, right? That is many, many levels below the semantic level that we wanted to operate at. And I think one reason that we don't take a kind of more AGI approach to building a system like this is we're not patient enough to build a system that where it could learn all of those layers, so that it really could operate at that lower level. There would be tremendous advantages if there was a more uniform thing. Right now, the different components of CALO, we have to figure out how to integrate them. And if you interrupt one thing you're doing to gesture with your mouse at something else, this isn't apparent at all in the user interface. So the fact that you use multiple windows and they're open, I mean, window focus is kind of a way of signaling which thing you're working on at any point in time. But I would say anytime you have to change windows on the desktop, that's actually a signal that the user interface is failing. There should be some way of doing what you want to do where you are, and not having to make the user explicitly indicate the context. But the advantage of these function-specific user interfaces is that the actions the user does, like opening a file and sending an email message, these correspond to very high-level user interface things that we can instrument inside the Microsoft operating system or the application. And the same applies, of course, to acting. The low-level actions are things like painting pixels and changing bits on the disk, and maybe on the network output. But we want to do things like pop up, checkbox list or something. A third argument you might make is that the different functions require different learning methods, although I think this is a weaker claim. But certainly, calendar scheduling is about preference learning, whereas programming by demonstration is much more about procedure learning. And so it tended to be that the different submodules had their own learning mechanisms in them. But one could argue that, and we've seen that presented today in several talks, that maybe there's a unity here that was not, that is lost in this modular approach. Okay, well, of course, the main problem with a modular approach is now you have to, if you're going to have any kind of integrated intelligence, you need to have, you have to integrate across these modules. And so that's where some of the more interesting research happened in CALO, I think. So let me show you examples of information flows between modules, integrated reasoning between modules, and then integrated learning. Integrated learning, by which I mean, if you provide feedback to one application or one module, it really should influence, sort of in an agent-wide way, CALO's knowledge of the world. Okay, well, point-to-point, so information flows in CALO were basically point-to-point engineered information flows. So someone said, oh, well, you know, a cool thing about the prep pack is that we could probably use the words in the documents in the prep pack to bias the language model when recognizing the speech, because the speech recognition had about a 30% word error rate. And if we had some idea what words were going to be mentioned in the meetings, we could bias the language model to look for those words, like the names of the people that are going to be there, the names of the projects, things like this. And so we did that, and that was basically put in as once a prep pack was created, it was sent off to the meeting assistant. No general purpose way of doing that. Similarly, at the end of a meeting, then meeting action items could be added to the to-do list. This was done again by sending a message from one component to another. And we saw a third case, I guess. Iris, the desktop sort of information manager, is trying to figure out what the roles of people are on projects. Emma, which is the calendar schedule, when it comes up with an unsolvable set of constraints, it just can't find a meeting time where everybody on the project can attend, it tries to figure out, well, who are the important people on the project? And it can do this, well, Iris can do this by saying, well, some people on this list of recipients have never sent an email message to this group. They're always just lurking. They're just receiving mail, but they never answer it. In fact, maybe they never even read it. So they're probably not the ones. We could probably schedule the meeting without them. And so that was the idea. And so another point-to-point connection was created. So, of course, the big problem here is all these are just manually engineered. We had no general way for CALO to say, oh, it would be really great if I could do X with Y, and I should put a connection in there. Okay, let's move on to the integrated reasoning architecture. So for a subset of the components that all dealt with people and projects and so on, we had an integrated sort of state estimation architecture. We divided the things that CALO needs to know into things that were in we call the knowledge base, which are basically indefeasible facts. So interpretations of primitive events, or just the primitive events and the primitive objects, which we can directly observe in our setting. And one thing we know about those is those are all mutually consistent, right? And then there was the probabilistic knowledge base, which were all the facts that we were uncertain about. So our interpretation of those events, things that we had learned, the predictions coming out of classifiers and so on. And for this we used Pedro Domingos' Markov logic as our representation, which is a probabilistic first-order logic. Well, almost first-order logic, let's say. And of course, so then with things like learned classifiers, like the document classifier and so on, what they do, what you can view them as doing is pulling information out of the knowledge base and the probabilistic knowledge base and then asserting their predictions into the probabilistic knowledge base. And then we had a Markov logic reasoning engine, which we called the probabilistic consistency engine, which would compute the most probable consistent set of beliefs. So it's looking for the MPE, as it's called, right, in probabilistic reasoning, the most probable explanation for the observations. And it also computed the marginal probabilities of each of these. But then there were other components of CALO that were unprepared to deal with uncertainty. So we would also just publish that most likely explanation as if it were the truth, as just a propositional database, and export it to those components. Oops, and there's the user too. Okay, well, let me say a little bit about Markov logic, because I'm going to use this in an example in a moment. So in the knowledge base, we would have things like, a file like report1.doc was attached to email message 1. The recipient of email message 1 was Ray Perot, who is one of the managers on the project. The sender, he sent another email message, email 2, and the user said that the project for email 2, it should be the CALO project. So those are all actual sort of sense data. And then in our probabilistic knowledge base, we had some rules for associating projects to things. So one is that if a document D is attached to an email message E, then if P is a project of E, it should also be a project of D. So the projects of documents and their email messages should be the same. And similarly, for the sender of an email, if H is the sender of an email message and H is associated with project P, then the email message should be associated with project P, and if and only if. And similarly for the recipients of email messages. And all of these, in Markov logic, they're given weights, which are a bit like the weights in a logistic regression. They're sort of log transformed probabilities. And then that's a reasonably high weight, 2.2. And then user feedback shows up as we give it a weight too, which is higher, which says if the user says email E belongs to project P, then email E really does belong to project P with some probability, say with a weight of 2.94. Of course, the user might make mistakes sometimes, and so we can't trust them completely. And then we have a preference here that typically, each email message has only one project associated with it, and the same for documents. And also, this is an example of an output from a classifier, which a document classifier predicted that report1.doc actually belongs to the promotion and tenure project, P&T, and it assigns that a probability which gets turned into a Markov logic weight as well. So this is a very small Markov logic knowledge base and database, and let's then look at what happens inside CALO. So as an example of integrated learning, I'm going to look at this email message stream here. So this is an email message from Ray Perot to me, in which he says here, you probably can't read this, but I received your report. And he was replying to an email message where I had sent him my second quarter report. But unfortunately, CALO predicted that this email message actually belongs to the promotion and tenure project, which was another thing I was working on at the time. The user can correct this, of course, and say, no, this actually should be assigned to the CALO project. But what's interesting is that the mistake is not the email classifier making a mistake. It's actually due to the document classifier having made a mistake, and then that information being propagated by the Markov logic engine. So let's look at the reasoning chain that occurs. So first of all, the user creates report1.doc, and the document classifier tries to classify it, and this is the mistake. It says, I think this is something to do with promotion and tenure. Then the user, that would be me, creates an email message and attaches report1.doc to that email message. So now the attachment rule fires, and it says, oh, well, that means email 1 belongs to promotion and tenure. Of course, when I say the rule fires, I really mean Markov logic, which having the rule decides that the most likely state of the world is one where where the email message 1 belongs to promotion and tenure. Then into the address line, I say, I want to send this to Ray Perot. So now the recipient rule fires and says, oh, well, Ray must have something to do with promotion and tenure. Then Ray sends me an email message, email 2, and now the sender rule fires and says, oh, well, email message number 2 must also have something to do with promotion and tenure. Meanwhile, I get that, and I say, no, email 2 belongs to the CALO project. And now the single project rule fires and it says, ooh, I have this conflict here. I have an email message that seems to belong to 2 different projects. So, of course, if we were using a sort of simple logical reasoning system, not the one that Stu mentioned this morning, we would get a contradiction here and we would have a problem. But we're using Markov logic. And so in Markov logic, right, the interpretation of Markov logic is that it is a probability distribution over possible worlds. In each possible world is a consistent set of facts that is a sort of candidate model for the statements in the Markov logic. And the score of a possible world is the sum of the weights of all the grounded forms of all the logical formulas that are true in that world. And so that can be converted into a probability by taking those scores, exponentiating them, and then normalizing them to get probabilities. This normalizer, though, is something that's intractable to compute because you have to score all possible worlds and then add up their exponentiated scores. Fortunately, we're only interested in the single most possible world or most probable world, and so we can do that without computing the normalizer. So let's score some possible worlds here. So one possible world is that we have an email message that genuinely does belong to 2 different projects. In that case, this single project rule is being violated. Let's see, how can I get my pointer to always be there? I think, some way I can do this. I guess I have to do it over here. Well, maybe I've got it now. And so that gets a score of 10.93. Another possible world is that the user made a mistake, and that even though the user said it belonged to the CALO project, maybe that fact is actually false. In which case, this world has a score of 9.72. And another possible world is really that the document classifier was wrong, and that the email all the inferences we made about the promotion and tenure project were wrong. And that is the most probable world. It gets a score of 11.27. So, of course, there are additional things that are true in this most probable world. Based on the user input rule, the sender rule can fire in a sense and say, oh, well, then email 2 must be, then Ray Perot, because he was the sender of email message 2, he must belong to the CALO project, which would be a very good idea because he was the principal investigator. And then, of course, he was the recipient on email 1, so that means, oh, email 1 must have had something to do with the CALO project. And this file, report1.doc, was attached to email 1, so it must have something to do with the CALO project too. And what's cool about that is that actually provides a training example back to the document classifier. So the document classifier gets the feedback that it was wrong about its classification. So this is our the picture that we have is that we can think of at the level of learning that our learning system actually has a set of training examples. In this case, our document classifier has a set of training documents along with their labels. And the labels are actually drawn out of the most probable beliefs from the consistency engine. So when the user provides that feedback, we eventually conclude that the project of report1.doc is the CALO project. So that becomes a training example for the document classifier, which then updates itself and gets better. And what's kind of fun is that it turned out, this was sort of an unanticipated benefit of this, is that if we have multiple classifiers, the email classifier and the document classifier, they can train each other in something we call relational co-training. Because of this, whenever a document is attached to an email message, the rule that says, well, their labels should be the same is a way of propagating then a label on a document to a label on an email message or vice versa. And so you end up with this kind of loop. Once we know the report1.doc belongs to the CALO project, that gets asserted into the probabilistic knowledge base with some weight. Then the attachment rule fires and says, oh, well, then email 1 must belong to the CALO project. And so that provides a training example for the email classifier, which then can go off and classify some other email message, which maybe has another document attached to it, if we're lucky, which gives us now a training example for the document classifier, and so on. And we can go round and round until we arrive at a consistent interpretation. And this is actually turns out to be an instance of the EM algorithm, if you think about it properly. And that's why it's underneath these things. But these are weighted training examples now. They come in with the probability that we believe them so that their influence is not too high. Okay, so what are the lessons that we might take away from this? One is that the point-to-point integration can be effective if we're willing to rely on engineers to identify the need for point-to-point communication and implement it. So that's really stepping outside the architecture completely. Multiple state estimation components can work together with a probabilistic reasoning system at the core, and multiple learning modules can be integrated via probabilistic reasoning as well. But I'd say there are 3 problems here. The first is we have to rely on engineers for the first thing. The second thing requires that we assume a shared ontology across the entire CALO system, which is really a kind of violation of modularity and was actually a humongous headache, right? Because it usually took, whenever you made any change in the ontology, it had a ripple effect on all of the different modules that were using it. And so naturally everybody's very resistant to making any changes. And so the ontology basically becomes a huge hindrance to system development and maturation. And the last thing is, of course, at every step we're doing this very expensive probabilistic reasoning, global probabilistic reasoning in Markov logic, which it was very painful. So so I would say there's plenty of room for improvement here, but I think we were able to show some integration across the different components, and in particular this kind of end-to-end learning where you can provide feedback to one thing and that feedback travels and informs other components of the system was pretty cool. Okay, well, what was missing in the system, and how am I doing for time? The first thing is, well, what's missing? So the first thing is metacognition. So CALO had no reflection capability. And this means it didn't really know why it existed. Of course, it was a personal assistant, but it didn't know that. So it had no model of its own goals. It had no model of what it did or did not know. And it didn't really have any model of what it could or could not do, right? Because it couldn't introspect on what actions were available. I guess in some simple sense, it could introspect on its knowledge base. It could enumerate it or something. But as a result, CALO couldn't evaluate how well it was doing, right? It couldn't notice patterns in its own failures. We detect that they were failures, first of all, and then look for patterns in them, and then develop approaches to fixing them. It also couldn't notice user errors. I'm not sure reflection would have allowed it to do this, but maybe a theory of mind and some idea of what the user's goals were would have allowed it to say, oh, the user just forgot to CC this person. Okay, well, we as engineers said, oh, you know, people sometimes forget to CC people, so let's write a module that does CC prediction and add that into CALO. And we did that. And I think Google now, Gmail, might have a thing also that looks to check that you maybe are sending the message to the wrong Tom and things like that. But again, CALO should have come up with that idea on its own. It says, I see the user making a mistake. He's sending this message to someone who's not related to this project. I wonder if that's a mistake, and maybe I should intervene. Or the user, well, actually, we worked on a use case where the user is sending an email message that should be marked as confidential and forgets to mark it as confidential. And so we had a way for the user to program CALO by demonstration that it wanted CALO to learn to detect that mistake. Obviously, the standard use case is you forgot to put the attachment onto the email message before you sent it. So overall, CALO lacks the ability to formulate its own new learning tasks and figure out how to solve them. So it's got some set of learning goals that are sort of given to it by the engineers, and those are the only ones it has. The second thing that's missing is any kind of automatization or skill acquisition. So, really, most of what CALO is doing in terms of its probabilistic reasoning is routine reasoning, which it is repeating over and over and over again. And it really should become faster with practice. So, I am a huge fan of the SOAR architecture, and I was really intrigued by Sigma this morning. And this idea that a system should become faster as it works, I think, is critical. In fact, I suspect it's critical to making any system like this really scale and operate well, and do state estimation and action selection efficiently. The third thing was any kind of smart memory model or any kind of smart forgetting. So, the questions I was asking this morning are the ones, these are all the things we did wrong or just didn't have time to address. So CALO saves absolutely everything. Partly this was to support debugging and support experiments and research, but it meant that every file that on your disk, it also made a copy of it, all your emails, every observed desktop event, the raw speech files from the meetings, and so this means it can only run for about a week or maybe two before it completely fills the disks and memory and grinds to a halt. In addition, CALO doesn't have any kind of episodic memory, so it has this sort of lifelog style memory of just sort of the raw transcript of your life, but it doesn't organize that into any structure that could be indexed and easily queried to answer questions. Instead, it's really only maintaining a model of the current state, and if you wanted to reconstruct some past state, you would really have to rerun your life forward from the date of birth until you get to that point, and then you could answer your questions. So I think there's a huge need for sustainable AI, by which I do a lot of work in ecology, but that's not what I mean here. I just mean that the thing could actually stay alive for more than a week. And that means, all the learning needs to be online, whereas we were using a lot of batch learning. And you need to live with a fixed amount of memory and really take that seriously. Maybe your external memory can grow, but the core memory needs to stay there in order to keep the system efficient. Okay, well, let's speculate a little bit about if we were rebuilding the CALO project and in an AGI mindset, what might we do? Well, I think it's a really interesting question to ask whether you could build a unitary CALO. I mean, obviously, the kinds of things it's attempting to do are a lot more complicated than the kinds of things we've been seeing in a lot of the talks here today. we would need to model all of our actions in a single action language, and maybe that's not too difficult. We'd need to have some unified utility function of what both that includes what the user is trying to do, and then also the fact that CALO is trying to assist the user. And some colleagues of mine actually published a paper, I think at AAI or IJCAI, maybe 2007-ish. This is Alan Fern and Prasad Tadapalli, where they put forward a model of what that would look like. I think in the CALO case, you'd really like the system, since customized user interfaces really are a key component of good interaction with the user. It should have the ability to design user interfaces and to improve them. And there has been some work done in the HCI community, at least on customizing user interfaces. And there are lots and lots of issues with moving buttons and driving the user crazy. So there are definite costs there. But of course, you know, here I am with my iPhone on my trip, and I have a very expensive data plan when I'm overseas. One of the things I want to do is monitor how many megabytes I've used. That's like 4 or 5 menu items deep in the user interface here. I want it to be, you know, where I can see it every day. Now, I hear that on Android you can pull things up like that to the top level, you can see them. But anyway, that's the kind of thing that you know, the demanding users are demanding. Another question is dealing with the ontology. So the ontology right now was hand engineered, and as I said, it was a real source of brittleness and bottleneck in everything. So we really need. Well, maybe we dump the ontology in some way. Maybe it's something that could be learned by demonstration. Maybe it could be optimized by the system itself. And then, of course, there are this challenge of having some sort of core reasoning system that could deal with time and equality and I would argue probability. But it also needs to be coupled with some sort of skill compiler or chunking mechanism or something that allows it to automatize routine inferences. And then everything, I think, needs to be teachable or learned rather than being programmed. So it's a huge challenge, and maybe that is the kind of thing that we seek to do. Well, I think it is the kind of thing we seek to do. I think it's also interesting, though, to ask, what, on the other hand, could we build a fully modular CALO? Which had no global ontology and no global inference, but instead was really sort of fully distributed modules. So I'm also a big fan of the Society of Mind kind of view of Minsky's, in which it's easy to sort of add modules to a system, and they learn to be members of this sort of this community of modules and work together to solve problems. So that means that they can have, each module can have its own ontology, its own representations, and then they must talk together through some syntactic interlingua rather than through a set of symbols where it's assumed they have agreement about what they mean. And instead of having a global reasoning system, then global reasoning starts to look more like argumentation or discussion, where the different components talk with each other and try to reach agreement, and they form models of each other. Like you know, Tom's not very competent. I can't really trust him when he says he'll do things, and so on. And so I think the question, of course, with any modular system is how can it learn to act quickly and in a globally consistent way while still having this distributed kind of architecture. But the big advantage, I think, is that for building systems, it would be nice if we could build them in a very modular way. So, you know, I've kind of set up this talk as a view of some design trade-offs. Where on the one hand we had this modular architecture, and the advantages, the blue bars here are purported advantages. So we can do separate engineering, and we can add and delete functions easily. And then since state estimation is done separately in each module can do it on its own efficiently. On the other hand, integrated state estimation becomes very difficult. That's this here, and Meta-Cognition. Well, maybe it becomes almost impossible because the modules don't know what each other are doing. So then, whoops, my reveal here was that I would argue that we did address one of these blue bars by showing how we could do integrated state estimation and learning using Markov logic. But of course, the solution is still expensive. So you might argue that it's only a half solution there. So it would be interesting in terms of a research agenda to say, well, let's look at each of these red arrows and ask, you know, if we're going to go for the unitary architecture, then can we still achieve kind of ease of engineering within a unitary architecture? Can we achieve efficient state estimation and action selection that maybe only requires local reasoning within a single unitary architecture? And if we're going to go with modular architectures, then I think we really have a big challenge in thinking about metacognition and how we could do that in a modular way. And I think that's what this slide said, except there are some cross-cutting issues. Regardless of which modular versus unitary you choose, automatization is an issue that has to be confronted, sustainable memory management, and then system building by learning or development and or evolution. How can we avoid the expensive engineering that we're doing these days? Okay, so in summary, so CALO was a personal cognitive assistant. Some of its attributes, let's say, that, where it had a global ontology and a modular architecture, engineered point-to-point information flows, integrated state estimation, and integrated learning for a subset of the components. But it lacked metacognition, automatization, and any kind of sustainable memory system. So, of course, this was the work of probably 200 plus people, and so these are mostly the faculty that were involved. Of course, there was a huge team at SRI International, and then people at many different organizations. And I'm required to point out that all of the opinions expressed in this talk are my own, and in no way represent the opinions of the U.S. government or any of its subparts. Questions?
Do we have a micro somewhere?
Oh, yes.
Oh, yeah.
There. No? Still got the red line on.
Perhaps this one is green.
Green is good and red is bad. No, but I know, but on this microphone.
Okay, thank you for a very interesting presentation, which is really very intriguing and exciting, but I still have two questions. The first question is about the relationship between the CALO system and the natural language processing or machine translation. Because emails are routinely written in natural language, and the natural language are something very hard to handle. Yes. Some people, their English are very poor. They will misspell something. And we can even suppose a case in which email is written in non-English, in Chinese characters.
Right.
And that can I'm curious about, is it necessary to add a new module to it, NLP module or MT, machine translation module, into the actual? I'm not sure.
Right.
The second question is about the size of knowledge base. You have mentioned that the current CALO system is not good at smartly forgetting something. That means it should keep its knowledge base as the same. From the philosophical perspective, it seems that the KB looks like the conceptual truth, and the probability KB looks like the empirical truth. So, how big the KB should be? I will give you an example. For example, President Obama gave an email, and he never gave an email before. So there will be great chances for my current email system to regard this email as a spam email. But it's a mistake, and I will manually correct it. Because in my knowledge base, I know that Obama is so important. I cannot ignore him. So is it possible to equip CALO with such a huge knowledge base in which maybe an encyclopedia will be embodied in order to avoid mislabel something as a spam email? Thank you.
Yeah. Well, those are both very good questions. And I think you can see that for the natural language, we mostly try to avoid doing natural language understanding. So there's a very limited amount the closest thing was in the PLOW system, of course. There was a very deep natural language understanding over a limited domain. So this is James Allen's work on, and he's been developing this system called trains, basically, that for 20 years or so. And so it's a very sophisticated natural language system. But again, the the grammar and so on is well, it's not exactly, the grammar isn't exactly customized, but the vocabulary and so on is really task specific. So there's a lot of engineering involved. Outside of that, we did attempt to do some simple speech act analysis of email messages, like, was I informing you of something? Was I requesting something? Was I replying to a request that you had made to me? Because that was an important part of some of the workflows. And then in the meeting understanding system, again, they tried to understand instances of people agreeing or disagreeing, reaching a decision, things like that. But it was mostly a kind of word spotting and topic analysis, which because it had to tolerate 30% word error rate or something like this in the speech transcription. So I think the answer is that I think CALO could be a lot better assistant if it actually could understand your emails, which it really isn't. It has a very primitive understanding of them right now. Yeah. Let's see. And then your other question was, would it be good for it to have more world knowledge? Absolutely. I mean, that would go with deeper understanding of emails. Yeah. I mean, I have gotten emails from Obama, and they were spam, so... But they should figure out that he is so much more important than I am that it can't possibly be really for me, right? So it must be spam, especially because he's asking for money. So.
My question is regarding a similar problem that that gentleman asked. That is, if you have built up a knowledge about this spam email, for example, just using spam email as an example, and then you have a strong belief that this email is a spam, but then later on you correct it. So the act that you corrected actually should carry more weight to the learning algorithm. So, so the way I see as a solution to it is not about how you build up a more sophisticated understanding of the world, but instead maybe from the approach of the learning algorithm itself. So I think, is this an incremental learning problem?
Yes.
And then how would you tackle with this problem?
Well, what we were using in the system from what I showed you was a simple support vector machine classifier. We've now moved to something that's called the confidence weighted classifier, which is some work by Kobe Kramer, and it's an online algorithm that does what are called, he calls it a passive-aggressive algorithm. So it's passive like perceptron in the sense that if it's already getting something right, it doesn't do an update. But if it's wrong, it's aggressive, and it does an update so that it would not make that same mistake again. Whereas perceptron or naive Bayes would take a little step in the right direction, kind of a gradient step. It takes a big step. And that really improves the user experience, because otherwise you correct it once and it says, well, okay, I'll add 1 to my counter of that, but I have all these other evidence, and so you have to keep telling it, no, you keep making mistakes until you drive the statistics up to the point where it will actually listen to you. So I really love it. In fact, that part I have running on my laptop right now, where every email message that arrives gets tagged with tags for the various projects that I have. And I find it extremely accurate. But when it makes a mistake, it completely tries to correct it immediately. Yeah.
Can you repeat the...
Oh, it's called confidence weighted, or CW. And then there's a version of it called AROW, AROW. And those have been published either in NIPS or ICML or AAAI. Yeah.
Thank you.
Sure.
Thank you for your talk. I'm really curious with this problem. The ecosystem you were talking about, this computer desktop, I think it's slightly older than me already, or we are same aged if we are taking the Xerox work into account. And you were addressing really really tough problem of assistant, of computer-aided assistant. But when I was learning this traditional AI approach, my mobile phone already got so many sensors, so it knows where am I, what are my plans are, and so on. So having so many instruments, having so many tools, including scheduling, to-do lists, including emails, and so many sensors as geolocating, as all the data from different channels. Why does not it produce even simplest forward chain inference? Because so many simple information chunks it already have, it can infer for me. For example, such simple tasks like to give me alarm that I'm asking maps for route to home from a different location, and it can allow me that there is a general store on my way, and I have remember the milk task in my to-do list.
Right.
And it could be done years ago, and I don't think I am the first one who have this idea.
Right. Yeah.
And why does not anyone produce such a product? Yeah.
Great question. I think one reason is that neither the desktop nor the phone top, the telephone, neither of them have been designed with an instrumentation and effector layer in them, so that it's very hard to write a program that can look at your to-do list, look at the map, look at your alarm, and notice things like, oh, Tom, you're always 5 minutes late for this meeting. You should leave earlier. I should set your alarm to wake you up 5 minutes earlier so that you get there on time. And it really, as you say, it has all the information it needs for that. And yet, but the trouble is, just like on the desktop where you have your one set of information in your email application and another in your web browser and another in your calendar, on the phone, it's similarly not integrated. It's better integrated than it was in the sense that there is a protocol, but you can't add, like we've been thinking about, how can we build, a sort of a CALO phone connection so that when I read my email on my phone, I can get the classifications that I'm getting on my desktop. It's almost impossible. It's really much harder to add any kind of user interface elements on the phone than it is on the desktop. So it'd be great if, operating systems and user interfaces of the future had an instrumentation layer in there and a cross-application communication layer. And then a huge security layer, because the security risks of this would be immense. But, yeah.
Being such an expert in this field and having such projects done, what will you propose? How do we reach this goal? And have you any roadmap that could lead us to it? Thanks.
No, I guess I don't have a roadmap. I mean, I think it would be interesting to try to follow up on some of the things from CALO in terms of the discussion in the last part of my talk. So that's the closest I have to a roadmap. Is I think that these kinds of applications pose a big challenge for either the unified architectures we're developing, or if we want to try modular architectures, maybe even more challenges. So. As it is right now, we just spend a huge amount of money knowledge engineering each new system, and we don't seem to gain anything from one system that we can transfer to the next. Except we're starting to accumulate some knowledge bases that are reusable, so that's certainly a good step.
Are there other questions, comments, please?
Thank you for your presentation, and I have a question, and that is, learning the preference of a user is a difficult task. And then, have you ever tried to combine the non-preference information and the preference information to improve the system's learning results? And what techniques are you have used?
So have we tried what? So what would be an example of non-preference information that we would want to include?
For example, an email, and an email have many topics, and maybe I listen topic, for example, the buying something or something, the lecture or the course, and then I don't like the topic of the advising or something else that I can using this information to improve the result of the rationalizing the spam email.
Well, I think the closest thing probably would be in the calendar scheduling application, because there was a inference engine inside that, which was a constraint solving system that had both hard and soft constraints. And so the hard constraints might come from what meeting rooms are available or the time that the caterer can arrive with the coffee. And then the soft constraints would be the preferences of individual people for meeting times and so on. And of course, there's another. All of these optimizations actually are multi-criterial. So one of the problems with scheduling is what happens when the schedule slips. Like the visitor is actually late arriving, and so everything has to change. And so that was another thing they looked at. Was, I mean, a good human scheduler would add some free time or slack time so that there would be a chance to catch up, right? Or a meeting that could be optional and could be canceled if necessary. And so you would like to have that in the system too. So I think you're right that when you really dig into preferences, they are very complicated. And this is probably why most existing calendar scheduling systems are not very successful. Their users generally hate them. And and I think it's because they're not expressive enough to really capture all of the preferences people have. And the same, I think, is true for a lot of the shopping. Yeah, I mean, it seems like a simple online shopping query often takes you a long time to actually get down to the thing you're really looking for, because there's so many other things. And of course, it's adversarial. People selling things are trying to trick you into buying their product instead. So it's really difficult.
Okay, thank you.
Well, this may be a very specific question, but on the example of the miscategorized series of emails between you and Ray, there was one rule that I didn't hear you question in assigning probabilities to alternate situations. That is the rule that says an email with an attachment, the email is on the same topic as the attachment is. And I can imagine that being
Can be well, it was a soft rule.
So one could give, you know, a document that's an example for a natural language understanding system, for example. So did I just miss that?
No, well,
or was that put in a place that was non-defeasible, or?
No, it was defeasible. So the attachment rule was a soft rule also. So that's another. It would be another one of those possible worlds, is that the attachment rule should be ignored in this case. Yeah, but I think I manipulated the numbers in the example so that would not score as well. And actually getting the weights on all those rules right really requires a training set, and then training Markov logic, which itself is also very expensive. I had something else I was going to say there, but oh well.
Other questions? So perhaps I ask a very, very short question, just because I'm curious. So you can be interpreted as someone who is arguing for a pluralism of methods, right? So
yeah. I mean, when I'm over here, yes.
Nevertheless, you use very specific methods. So you, for example, Markov logic for the reasoning, and for example, the support vector machine for certain classification tasks. And probably your underlying ontology was also formulated in a very specific knowledge representation formalism, as it's usually the case, and so on and so on. So did you have any specific reasons, for example, to use precisely Markov logic for this reasoning task, and not another type of probabilistic approach together with logic or some fuzzy logic or whatever, or concerning the learning, the classifiers? So are there deeper reasons for doing this, or was it quite accidental because the right experts were around, or you had already a ready-made tool for that?
Well, actually, we were funding 3 different probabilistic logic efforts, and we chose Markov logic because we were going to use rule learning to learn the rules, like the attachment rule and so on. The other formalisms were blog, and I'm trying to remember what the other one was, but which are directed probabilistic models, and which would mean we'd have to think carefully about the directions of the rules. And since the rules were themselves going to be learned, Markov logic had the advantage we could just throw them all in, regardless of where they came from and what sort of they were kind of a-causal or a-directional, and then Markov logic, in theory at least, would make it all work for us. But the one thing I did not appreciate about Markov logic that maybe I would change my mind is, in Markov logic, all of the weights are coupled in the system, so the probabilities are completely non-modular. It's just like the difference between, say, naive Bayes and logistic regression, is that in naive Bayes, the statistics can be calculated completely independently of each other, and in logistic regression, it's a global optimization. And Markov logic is a global optimization, and that makes it very non-modular, and it makes learning very expensive. And whenever you add another rule, you have to retrain the whole thing. And I think that's a disaster, personally, although, I mean, it's so elegant, but I don't think it's, I think we need to explore more ideas there. Yeah.
Are there further questions? If not, it's 7:30.
Is our next?
So I have to thank, or we have to thank our speaker once more again.